Today we're going back to splitting into two lectures, lectures 24A and 24B. And this week we're going to be combining a couple different topics. We're going to be combining optimization problems with differential equations for the most part. In 24A, I'm going to start by talking about optimization terminology in a visual way. I'm going to draw things on the board. I'm not going to write down precise definitions, but it's just instead just try to give you an intuitive idea about the terminology with optimization. That's going to generally be good enough for us. I will eventually write down some more precise definitions, but initially we'll just make some drawings. I want to review the surface area minimization problem from last time and talk about it in the context of Mathematica programming, because of your project you're going to have to use Mathematica to make some animations, for example, or graphs. Then in lecture 24B, I want to do a couple more optimization problems and introduce a new topic of differential equations, which again I want to talk about both optimization and differential equations this week and probably next week too. Okay, so what I've got here on this slide is going to be a bunch of terminology, and I want to talk about this terminology with drawings. So the first idea is the idea of a local extreme point. And by local extreme, it could be a local maximum or a local minimum. Extreme means max or min. That's the first thing to realize. Local means it's a high point or a low point of a graph locally, nearby the given point. It could go higher or it could go lower, far away. But if you're close enough to the given point, it's a high point or a low point. So here would be an example of a graph and a location where you might have a local maximum. It's a typical kind of graph with a local maximum. So this point is supposed to be the high point of the graph nearby. Again, the graph might go higher over here. That's why there's an emphasis on the word local. This will be a local maximum point. There's a certain value where that local max is occurring. You could call it C. And that number, C, is an example of a critical point. A critical point. That's why I'm calling it C, C for critical point. Here the critical point is a number, not a point in the usual sense. However, it is associated with a point that's got coordinates on the graph at C, comma, f of C. And that is also called the critical point. And the book emphasizes that you can think of it either way. You can think of the critical point as either referring to the number where the local max or local min occurs, or precisely the number where you have a horizontal tangent line, or you can think of the point itself as being the critical point. The output of the function there, however, is not called a critical point. It's called a critical value. That's a critical value. The word value is used to emphasize it as being an output of the function. Like a minimum surface area, for example. Well, this would be a maximum. Like the example from last Friday. You would say here that a local maximum occurs at the critical point C, and the local maximum value is the critical value. In this case, it is also a local maximum value. Again, emphasis on the word value. Think of that as referring to an output. We can switch the diagram around. We can have a low point. That would be a local minimum. C is still a critical point. And so is this point, as a point whose coordinates would be C, comma, f of C. These would still be critical points. I'll say it again. Both the number C and that point, that's the low point here where the tangent is horizontal, are both called critical points. F of C itself would be a critical value, again. But now you would say it's a local min value instead of a local maximum value. A local minimum value in this case. Can anything else happen at critical points where the derivative is 0? Yes, it can. You can actually have critical points that are neither local maxima nor minima, like with the cube root function, or with the cube function, y equals x cubed. As one example, at the origin here, you've got a horizontal tangent. That is a critical point. C equals 0. This is a critical point. However, it's not a local min or a local max, at least over this domain. Now, if you restricted your domain to say only considering positive numbers, then it's a low point. And that low point would occur at the left endpoint of the interval if your domain was only positive numbers. And if your domain was only negative numbers, then it would actually be a local maximum point. It would be a right endpoint of the domain in that case. But if your domain is all real numbers, or in fact any interval centered at 0, where 0 is not an endpoint, it would be a critical point, but not a local max or a local min. It's neither. Sometimes people call that a node. Sometimes people call it a saddle point. Saddle point is probably a better word to use if we generalize to higher dimensions, but it's not a local max or a local min. But again, the answer depends not just on the function's graph itself, but also the domain. You have to think about the domain of these things. Coming back to the screen here, so I've already talked then about critical points and critical values. Here's essentially a theorem. At a point of differentiability, remember what differentiable means, it means the derivative exists, which is not an endpoint of a given interval, that happens to be the domain you're thinking about. If the point is a local extreme point, either a local max or a local min, then the derivative will be 0. Okay, the tangent line will be horizontal. Again, look at the pictures over here with the camera. That's a local max. It's a point of differentiability. The derivative is 0. The tangent is horizontal. This is a local min. It's also a differentiable function. Tangent line is going to be horizontal. So if, again, it's a local max or a local min, the derivative will be 0 there. However, this doesn't go the other direction. If the derivative is 0, that doesn't mean it's a local max or a local min, by what I just said 2 minutes ago with the x cubed function. That's a point where that's a critical point. F prime of 0 is 0. The tangent line is horizontal. The graph looks more and more like a horizontal line the closer you zoom in to that point. But again, over the entire domain here of the entire real line, it's not a local max or a local min. It's not a point at the top of the hill or a point at the bottom of the valley. Unless we're, again, restricting our domain and only considering one-sided valleys or hills. We've got to use tests to confirm whether we truly have a max or a min. And there's 2 tests. There's the first derivative test, and there's the second derivative test. And again, you can write these things as theorems with real precise statements, but for the sake of time, today I'm trying to get across just the visual. Let's come back to these pictures. So here, it's a local max. You can just see from the picture what's happening with the derivative of this function. When x is to the left of c, you can see the graph is going up. Tangent lines have positive slopes. The derivative has a positive output. Over here, to the right of c, the graph is going down. Tangent lines have negative slopes. The value of the derivative is negative. So the first derivative test says, if the derivative changes sign from positive to negative, positive slopes to negative slopes here with this function, as x increases through c, then it's got to be a local max. Makes good intuitive sense. You can see it with the picture. If f prime is positive and changes to negative, as x increases through c, and you've got a critical point at C, f prime of C is 0, you've got to have a max at C, a local max. Coming to this picture over here, the first derivative test verbally says if f prime changes sign from negative to positive as x increases through C, then it's got to be a local minimum. Here, in this picture, neither of those things happens. F prime of 0 is 0, but f prime doesn't change sign. It's positive here, and it's positive there. If you were to graph f prime, in this case, it would look like this. It doesn't change sign. And what that means is the first derivative test does not apply. You can't use it. Okay? It only applies when it changes sign. When the derivative changes sign. So I'm saying this verbally. It's in the book in writing. We will probably eventually write these things down in the PowerPoints, but for the moment I'm just describing it verbally and with pictures. We also have a second derivative test. Before we talk about the second derivative test, we need to remind you of what concave up and concave down means. Concave up, I've said informally, is when the graph looks like a smile or a part of smile. Those are all concave up. Concave down looks like a frown and rhymes as well. How about that? Concave down looks like a frown. Concave down looks like a frown or part of a frown. These are graphs that are concave down. What's really happening? What's really happening is the derivative of this function is either increasing or decreasing. Here, think about it with me. Look at this graph. As you move from left to right, the slope of the tangent line is increasing from negative to positive. The derivative's value is increasing. If you graph the derivative, it would be going up. Same thing is happening here and here, though a little bit in a more restricted form. The tangent line stays negative the whole time, but it's getting closer and closer to 0 in slope. So the derivative is getting closer and closer to 0. It's increasing still. Here, the tangent line always has a positive slope and getting bigger and bigger. The derivative is still getting bigger. It's increasing. With concave down, the derivative is decreasing. The slopes are going from positive to negative, or becoming more negative, or staying positive but getting closer to 0. In all those cases, the slopes are decreasing. In other words, the derivative function has a graph that's going down if you graphed it. That's really what concave up and concave down means. When you're asked what is concavity, the question is the graph concave up or down? Or both, it can change. It can be concave up over some intervals and concave down over other intervals. The second derivative test is a test for local extreme points based on the concavity. Here, you can see the graph is concave down. At a critical point, that means that you're going to have a local max. The second derivative is negative. At this point and near this point, in fact. Here, the second derivative is positive. At this point and near this point, and this is a critical point. Therefore, that critical point has to be a local min. With this example, neither of those things happen. The concavity changes. Concave down here, concave up there. The second derivative is really changing sign from negative to positive. And it's 0 at the critical point. So the second derivative test does not apply in this situation. With this situation, neither the first derivative test nor the second derivative test can be used. It's neither one. Inflection points, very good terminology, are where the concavity changes. This point here is an inflection point in this graph. The concavity is changing from concave down to concave up. The second derivative is changing sign from negative to positive. Back in this picture over here, the inflection points are right about there, there, and there. The graph's changing from concave up to concave down to concave up again, and then back to concave down. Those are inflection points. Concavity changes. If you graph the second derivative as a function, it would change sign as x increased through these points. From positive to negative, positive to negative. If there's local extreme points, can you have global extreme points? Yeah, at least if you specify the domain. Although sometimes, if the domain is not chosen correctly, you might not have any kind of extreme points. And the simplest example of that is the graph of y equals x over the entire real number line. There's no extreme points to that graph, local or global. There's no absolutely highest point or lowest point. The graph goes on forever and ever in both directions. If I restrict the domain to some closed interval, like from 2 to 7, say, I'm still graphing y equals f of x equals x here. And if I emphasize that the domain is this closed interval from 2 to 7, this is the notation for it. The domain is that closed interval. Then there is a high point and a low point in the graph. That would be a global maximum point over this domain. I'm not considering any other real numbers as input. And this would be a global midpoint. Global does imply local. These are global, they're also local. Local doesn't imply global. There is a local max, it's not a global max. There's the most high point on this graph. This is both local and global in this particular graph. Global extreme points can occur at endpoints. And endpoints are not critical points in the way I've described so far. When you're talking about global extreme points, where is the graph absolutely highest or lowest? Those don't always occur at the critical points. If your domain is a closed interval, they could occur at the endpoints. You have to check the endpoints. How do you check them? You just plug them into the function and see whether they give you the highest or lowest value. And you can see it from the graph, too. You can make the graph with your calculator and see whether it's the highest or lowest value over the given domain. It gets a little funny if your domain is an open interval, though, sometimes. If I do not include the endpoints as part of the domain here, so effectively these points are not part of the graph anymore, that actually doesn't have a high point or a low point anymore. I should erase these here. Same function, slightly different domain. There's no highest point, there's no lowest point. You might be saying, well, isn't 7 still the highest point? No, because there's no point there on the graph. There's no point whose second coordinate is 7. So then you might wonder, is the high point 6.99999999? No. Because I can get higher than that. 6.99999. Add one more 9. How many do I have here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. I can get higher. You might wonder then, is 6.9 repeating the highest point? No, because 6.9 repeating equals 7. You may have heard that 0.9 repeating equals 1, and it's true. Don't ever let anybody tell you otherwise. 6.9 repeating equals 7. It does. How do I prove that? Well, here's my favorite little proof. Okay, wise guy, if they're not equal, what number's between them? You can't think of one. So they must be equal. And now my son, when he first heard that, he's like, well, Dad, couldn't you do 6.9 repeating and then a 5 at the end? No, that's not allowed. You can't do that. Okay? So 6.9 repeating does equal 7. Just like 0.9 repeating equals 1. There's even a Wikipedia article about point Niagara PD equaling 1. And I didn't like how it was written, so I actually made a Wikipedia account and I changed how it was written. And the guardian of the page didn't like what I wrote and he changed it back right away. I don't want to do it anymore. It was changed back within 10 minutes. And I'm like, they just didn't write it in the best way. That was the one page, because my son was confused about it. That was why I was upset about it, so I changed it. Anyway. All right, now I'm going to go over a summary of the optimization problem from last Friday. There's a lot of formulas on here, probably not worth writing down right now because actually we worked on last Friday. I'm trying to do a quick summary. My goal here is to remind you what we did and also relate them to the first and second derivative test. And I've got a couple slides where I've got the details of a real detailed explanation of how to use the first and second derivative test. You won't have to give such detailed explanations, but I thought it would be worth giving once for each test. Okay? So just listen. It's probably the best thing to do. So this was the optimization problem about the soup can, where you're trying to minimize the surface area for a given volume. Surface area formula for a sphere is 2 pi r squared plus 2 pi r h. The 2 pi r squared is the areas of the top and the bottom of the cylinder. The circles on the top and the top and bottom of the can. And the 2 pi RH is the area of the side of the can. Where R is the radius of the top and H is the height. We want to minimize that, subject to some constraint, that the volume is constant. And I call that constant C. Most of the problems you're going to do in the book, C would be something specific. I mentioned like 500 cubic centimeters last time. And that does make the problem easier to think about when you pick something specific for C. But I do want you to be able to handle more general situations because that's really where it's more useful. It's more useful to be able to handle more general situations because it gives you greater problem-solving ability for one thing. It also gives you more insight into what's really going on once you handle the more abstract generalization. On your project, that's going to be how you're going to be trying to get some extra credit as well, is by dealing with generalizations, not just your problem statement as is, but trying to generalize to some degree and make maybe animations based on that. Here are the initial details. Step one was to figure out, based on the constraint, how one variable depends on the other. I figured out how H depended on R. Right? I took the constraint equation, of this thing equals a constant, solve for H just by dividing both sides by pi r squared. Then, step two is a little harder. You got to plug that constraint fact into the original function, f, that I'm trying to minimize, in place of the h, so that you can get just a function of r. So that we can avoid multivariable calculus. I mean, I love multivariable calculus, but it's nice if you can avoid it. F depends on two variables. I'd like it to only depend on one. And the constraint allows me to see how it depends on one. If I didn't have that constraint, then it would just definitely depend on two. But I do have this constraint. The can just can't be anything. It's got a fixed volume. And that allows me to get that surface area in terms of just R alone. Of course, there's a C in there, but I'm thinking of C as a constant. Now that's a one variable function that I'd like to minimize. I'd like to find its low point. So I'd ultimately maybe like to use the first or second derivative test. To do that, I've got to find the critical points. I need to take the derivative, set it equal to 0, and solve for R. And here are the steps. There's the derivative. You can just mentally check that. I differentiated this thing here. I brought that 2 down to get a 4 pi r right there. I brought the negative 1 down there to get a negative 2c r to the negative 2 right there. Set that equal to 0, solve for r. A couple steps you can check out in class, like we did last Friday. You get this. That's the exact critical point that I labeled r sub crit. I'm thinking of this ultimately as a function of c for good reasons later on, though. So I'm putting an old c in there. It's this. It's approximately 0.54 times the cube root of c. C to the 1/3 power of the cube root. Does it minimize s? You really need to check that. Just like I suggested you do on your completion assignment, use either the first or second derivative test. The second derivative test, especially in an abstract situation like this, is a bit easier. We can use either test though. You don't have to use both. One or the other is good enough. The second derivative test is typically a little easier, especially in abstract situations like this, than the first derivative test. So that's why I used the first last Friday, but I think I have it on the next screen first today. I'm going to show the next slide in a minute here. Let's just go ahead and assume we've used it and it's a minimum. Step 4 would be to find this corresponding critical value of h to get the dimensions of that best can. What's the radius of the circle on top and what's the height? There's a can, a cylinder, there's R, and there's h. We'd like to find the best dimensions. What's the best value of R to use? What's the best value of h? That minimizes the surface area. And we might also like to find the minimum value of the surface area. What is the actual minimum surface area? I'd have to plug back into the function to figure that out. Complicated looking algebra. I'm confident you could do this if you just took it step by step. It turns out h is about 1.08 c to the 1/3. Interesting. That seems to be double this one. Is that an accident? No, it's no accident actually. And if you think about the fact that the diameter of the circle is double the radius, the diameter of the circle on top is double the radius, what it's saying ultimately is that the optimal can has the same diameter as height. Interesting. Most soup cans don't have the same diameter as height. They have other considerations to take into play though. And the actual minimum surface area, you can check by plugging in, and I skipped some steps here, is about 5.54 times c to the 2. Okay, again, you should check this after class. It would be definitely worth your while to make sure you can get this right. Worth your while, think of it in terms of the project. Can you do the project in the way that I'm suggesting? Again, I'm going to work on a sample project tomorrow. Here are the details of the first derivative test. And again, there's a lot to write here and too much to write in the time we have. I'm going to go through it pretty quickly. I suggest you look at it after class. I'll put it in the folder right after class here. And again, you don't have to write as much as I'm about to show you. Okay? I'm just trying to be thorough here, one time at least. How do you use the first derivative test? Well, the first derivative is that. It's a nice function. It's a continuous function for positive values of r. And because of that, that means it can only change signs at the critical point, or points. In this case, there's actually just one critical point when r is positive. There's going to be a low point in the graph. This is going to be what your generic graph looks like. S is a function of r. This is the function phi sub c of r. And there's going to be a low point. That's what it's going to end up looking for, no matter what c is. And the derivative is evidently changing sign from negative to positive as you pass through the critical point. And this number down here is r crit of c. It depends on c, so I could think of it as a function of c. And typically, when you have functions that don't have parameters like c in them, it's best to make a number line and mark off your critical points on the number line and test the sign of the derivative in each of the resulting intervals. We did an example like that last week as well. Check maybe that well, in this case, just at your critical point, check that f, or phi prime in this case, changes sign from negative to positive by plugging points in. However, because we got the c in here, it's like more difficult. So I can't plug in particular numbers and get something that doesn't depend on c. So instead, we could just think about it. When r is very small, 4 pi r is going to be positive and very small as well. 2cr to the negative 2 that other term is positive but very large because I'd be dividing by a very small number. So you'd have a small positive number minus a large positive number. That's got to be negative. The derivative is negative. You can give an argument for that. On the other hand, if r is big, then 4 pi r is positive and very big as well. And now this other term is going to be small because I'm dividing by a big number. 2c over r squared is the same as 2c r to the negative 2. If r is really big, like a million, I'm dividing by a really big number, it's going to be really small. I've got a large positive number minus a small positive number. That's going to be positive. So the derivative is changing sign with an argument here rather than plugging in particular numbers. And that means there's going to be a local min at the critical point. The local min is actually a global min when r is positive. Do you think you'd give a reason why? Even based on what I've said so far? The first derivative test only guarantees a local min. But I'm saying it's global. That's the low point, at least when r is positive. I'm not worried about what happens when r is negative because that doesn't apply to the situation. You can't have a negative radius. I only care about this part. Why has what I said there, why does it imply it's actually got to be the absolute lowest point? It's not really part of the first derivative test, but it should make intuitive sense because the derivative is changing from negative to positive. There's no way it could come back down again. That would be good enough. Good enough for me for you to say that. Let's quickly go through the details of the second derivative test again. Then we'll take our break. What is the local min value? You have to plug that into the function. I didn't actually find it, but you have to plug this back into the function for the local min value, the local minimum surface area, which again would be a global minimum as well. Here's the details of the second derivative test. Here's the second derivative. What's the second derivative test say? It says, or what are you hoping it's going to end up showing you here? We hope the second derivative is always positive. In particular, at the critical point, so the graph is concave up, so this is a low point. And this is just a brief argument that that's true. This exists and is continuous. It's 0 at the critical point. We've seen that already. Oh, no, the first derivative is 0 at the critical point, which is important to mention. And it's positive. It's certainly positive. 4 pi is positive. C, I'm assuming, is positive. R is positive. All I got, and I'm adding there, I got a bunch of positive numbers that are combining to give a positive number. And in particular, at the critical point, it's positive, which is really all you need. As long as that second derivative is continuous, which it is. So the graph is concave up near the critical point, and you've got a local min. And again, it's global. In this case, you can say it's global because the second derivative, when r is positive, is definitely always positive. This is true for all positive r. The graph is always concave up when r is positive. Okay? Let's take our break.